before starting today's class, I will introduce about the final exam logistics. Okay, so as I posted in the Blackboard, so we will take the final exam on June 20, the Thursday, and then during the regular class time. So the exam will immediately start at 10:30, and then this is important. So we will take the exam in Ujong Hall of Informatics 205. Okay, so not this place. Okay, so we will take the exam in 우정정보관 205. Okay, 우정정보관 205. Okay, so do not come to this room. Okay. So it is because this room is rather small. So even though we can find many empty seats now, but I believe so many students will show up for the final exam. So I reserved the larger room. So, and then also another problem is that, so the air conditioning is not good in this room, right? It's so hot. So we will take the exam here. So Ujong Hall of Informatics 205. Okay. Okay. And then the exam is the closed book exam, and then the exam will cover the chapter 3, chapter 5, and system law part. Okay, in chapter 4. Okay, and also the electric devices are not allowed. Okay, during the exam. So actually, actually we do not require complex arithmetic calculation. So we do not require calculator, right? And then any electric devices. Okay, so any questions? Okay, first.
Will be material before the midterms exam of the final?
So actually the final exam will focus on the chapter 3, so as I mentioned, chapter 5. Okay, so that's what we learn after the midterm exam. But so actually the FSM and then the sequential logic part also includes the combinational logic part, right? So it means actually, so in order to figure out some Boolean equations for FSM, then you may need to use kernel map, so like for optimization, right? So actually, so final exam will cover what we learned at the midterm exam, but actually you need to know about some combinational logic knowledge. Okay. Okay. Tuesday. So I will close the so this is the last class. So actually, so we will not have class on the next Tuesday. Okay. So this is the last lecture. Okay. Good. So you like it? Okay. So hopefully I can cover it. So as I planned. Oh, so hard. So in this in the previous class, so we learned about some various types of adder. So actually we focus on the delay of different types of adder, like the replicate adder, and then carry lookup adder, and prefix adder. And then so actually, so as I mentioned, the delay of arithmetic unit and then delay of combinational logic is so critical for the performance of the system. So it is because the propagation delay will determines the clock period, and then the clock period. So and then clock frequency is critical for the performance of system, and then actually the clock frequency is the inverse of clock period. So we need to reduce the clock period. And then actually, in order to reduce the clock period, we need to reduce the delay of combination logic. That's why we learned about the various types, like the three different types of adder. Also, this adder, the addition is the very fundamental arithmetic operation. So right, so think about your elementary mathematics course. So we first learn about the addition, right? And then actually the multiplication, division, and then also subtractions. So we can just derive these operations using additions. Okay, so we will learn also about the other three types of arithmetic operations, such as subtraction, multiplication, and division. But you can know that these operations can be built from basic adders. Okay, so that's why the adder is so important in the arithmetic unit design. Okay. Okay, so this is the very low code. So even though we learned about the very complex adder design, such as carry lookup and then prefix adder, but the Verilog implementation. Verilog implementation is simple, right? So we can use this plus operator like addition. So we can easily implement the carry propagation. It's a ripple carry adder, okay? And then, so this is another type of adder, but it's very simple. So actually, in a in the adder design, carry propagation is very critical. So it is because the carry needs to be propagated from the LSB to MSB. So it's just, so actually ripple carry adder, it's obvious. And then also for the carry lookup adder, so we can quickly calculate the carry out from the carry lookup adder block. But actually, the carries are also propagated between the carry lookup adder blocks. Okay, so carry needs to be propagated. And then in the prefix adder, so actually the prefix adder, the carry is also propagated. Okay, so actually we can reduce some required steps the prefix in the addition with some lower log scale. So because in the prefix adder, but actually the carry needs to be propagated. So this is the critical path. So we can apply some different idea. So this idea is the carry select adder. So the main idea of carry select adder is that actually, this is the some k-bit block, okay, k-bit adder block, okay, and then this k-bit adder block needs to receive C in, the K in, and then the K out is generated. But so we are learning about the digital system. So actually, the C in will have only two different values, right? 0 and 1. So what does that mean? Even though we don't know about the real value of this carry in, we can calculate the output of this k-bit adder using one of result. So it means we can generate the result for C in equal 0, right? So this is the case 1, case 0. And then we also generate some result of adder using C in equal 1. Okay, this is the case 1. Okay, case 0 and case 1. Then, if the carry is really reserved, so carry is really figured out, then we can just select from these two results using real carry value. Okay, so what's the benefit? So this adder, so k-bit adder, does not need to wait until the carry is reserved. Okay, it first generates two different results. Two different results using two different cases, like case 0 and case 1. And then after the result, the carry result is reserved, then we can select the result. So by doing this, this k-bit adder does not need to wait until the carry is really reserved. Okay, so this is the carry select adder idea. Okay, the carry select idea just to generate the two different results for carry 0 or carry 1. And when the carry is selected, carry is reserved, the outputs are selected. Also, the carries are selected. Okay, so you know, so in carry select adder, we can just cut the some critical paths. So carry propagation. We can cut the carry propagation. Then what is the disadvantage? It's cost, right? So you know, actually, this carry select adder requires the two adder unit. Okay, two different adder unit. So actually, this adder unit generate the result for C in equals 0, and then this unit generate the result for C in equals 1. So actually, we require the double of hardware resources. Okay. So actually, the disadvantage of the selected adder is the hardware resource overhead. Okay. So this is the some the organization. So the implementation of this carry select adder. So as I mentioned, so each k-bit adder block has the two different adder units, and then the first adder unit generates the result for carry is 0, and then the second unit generates the result for carry is 1. And then using the multiplexer, then the outputs are selected. So this is the carry select adder. Okay. So this is the end of adder. And then, as I mentioned, the adder is so important, right? And then, so now, we will discuss about the implementation of subtractor. So actually, so some students ask the question after the class. So they asked about why C in is required for the LSB, right? So actually, this carrying is also used for this add instruction, add operation, but actually the C in LSB is required for implementing subtractor. Why? So it is because, so what is subtraction? Subtraction is A minus B, right? But actually this is A plus minus B. Okay. So actually subtraction is equivalent to addition, but the second operand, the sign of second operand is changed. Then how can you generate this minus B? So we learned about the 2's complement number. So and then the computer systems use 2's complement number, right? So how can you make this minus B? Minus B equal not B, the bitwise not plus 1, right? In a 2's complement number system, so minus B equal not B plus 1. So which means that, so we can rewrite this equation like A plus not B plus 1. Okay, so this equation includes which one? Which part? 1. Okay, so actually, which means if we to perform subtraction, we firstly inverse the second operand, and then we can add plus 1. And what is this one? This one can be C in. Okay? So actually, so we can use the C in, the carry in of LSB for implementing subtractor. Okay? Okay, so as I mentioned, so the subtractor can be implemented using adder, and then actually, so this is the adder, but this adder is, so this is symbol of subtractor, okay? But the subtractor can be, as I mentioned, using adder, so this is adder, and you can find the inverter here, and then the C in, C in is connected to the 1. Okay, so this is the implementation of subtractor. So it's very simple actually. So if we can implement adder, then we can easily implement subtractor. Okay. Also in system Verilog, we can use the minus operator, the subtraction operator, to implement the subtractor. Okay, it's very easy. And then, but we know, we learned that we can implement subtractor using this NOT gate, and then the C is connected to high voltage is as a VDD. So which means we can implement the adder and subtractor logic in the same adder unit. So this is the implementation. So you can find the adder here. So this is the adder. Okay, it's the adder block, and then you can find the exclusive OR. Okay, and then also you can find that C in is connected to the subtract input. So if the subtract is 1, 1, if subtract equal 1, then this unit will work as a subtractor. And then if the subtractor is 0, then this unit will work as a normal adder. Okay, then how? So you can find the exclusive OR gate here. Then what is the truth table? So what's the truth table of exclusive OR? So you can find the B, and then it's a sum. So 0, 0, 0, 1. Okay, so it's B, and then it's a subtract, and then 0, 0, 0, 1, 1, 0, 1, 1. Then what is the result? So what is the output of this exclusive OR? This is 0, 1, 1, 0. So we can observe that if we just focus on subtract is 1, so this line and this line, so we can observe that B is inverted, right? So 0 is, if the B is 0, then it becomes 1, and then if the B is 1, then it becomes 0, right? So which means the exclusive OR means that if the sum signal is 1, it will work as an inverter. Okay, so do you understand? So that's why, so we use the exclusive OR gate here. So and then if the sum is 0, then it's the same. So it's a B, so 0 and so 1. Okay, so which means that it will work as an adder. Also, so subtract is connected to the C in, so it becomes the 1. So it can, if the subtract is 1, then it can implement the A plus not B plus 1. It's subtractor. Okay, so using this control bit, it's a subtract bit, we can implement the adder and subtractor using the same adder block. Okay, and then this is the system value implementation. So adder and subtractor. So you can find the two inputs A and B, and then you can find the C in is here. And then this is the control signal, the sub. If the sub is 1, then it will work as a subtractor. And then I just declare the internal node B in. Okay, it's not in, it's B in. Okay, if the subtract is 1, then B is inverted. Okay, so we can use also exclusive OR gate, but so I use some this ternary operator, and then we can just implement the adder like this. Okay, so you can find the B in is here, and then sub is just connected. So actually it's equivalent to this logic, this implementation. Okay, so we can easily implement the subtractor using adder, right? It's a simple. And then another arithmetic unit is equality check unit. So what is equality check unit? So if we can use the A equal B in C or suppose in Python, okay? We frequently use this equality check operation in programming, right? So the system or CPU also requires the equality check unit. And how? So we can also use the exclusive or exclusive NOR logic. Okay, so this is the equality check unit. So it means that if A equal B, then output is 1. So A is not equal to B, then Y is 0. And we can implement this equality logic using exclusive OR and AND gate. Why? So in order to check the equality of two digital number, then we need to compare the equality of each digit, right? So like the 1001, then A equal 10101, and then B equal 1001. Then in order to check the equality, then we firstly check the equality of this one. So equality of each digit. Then how can you check the equality? We can use the exclusive NOR. Okay. So what is the truth table of exclusive NOR? It's A, B, and then exclusive NOR output 00, 01, 10, 11. Okay. Then what is the output? It's 1, so 0, 0, 1. Right? This is the output of exclusive NOR. So this is because if we use the exclusive OR, then it's 0, 0, 1, 1, 0. Actually, exclusive OR is the not of exclusive OR. Okay? So you can find that if we use the exclusive NOR, if the two inputs are the same, then output is 1. Okay, so in order to check the equality, then all digits need to be identical. So which means, it should be 1, it should be 1, it should be 1, it should be 1. So, and then we need to use the AND gate finally. So this is the equality check. So in order to check the equality, then we can use this equality check logic using exclusive NOR. Okay. So why is the same slide? And then comparator. So in a programming, we also frequently use A is less than B. So if A is less than B, then blah blah blah. So which means the system also requires some comparator. Okay, and then this comparator just compare the magnitude of two numbers. Then how can we compare the magnitude of two numbers? So we can easily use the A minus B and then check the sign of the result. Right, it's a very simple mathematics. Okay, you have to check the A is less than B and is A minus B is less than 0. Okay, so which means in order to implement this comparison, then actually we can use the subtractor, right? So if using the subtractor, then we can implement this comparison. Okay, how? We can just check the sign bit of output. So I mentioned that the computer systems use 2's complement number. So which means if the sign bit is 1, sign bit is the MSB of the 2's complement number. So if the sign bit is 1, then it means it's less than 0, right? If the sign bit is 0, then it means it's larger than 0 or equal to 0, right? So because the 2's complement number, the 0, 0, 0, the 0 is also the sign bit is 0. Okay. So this comparator, we can implement this comparator using subtractor, and then we can check the sign bit, the MSB. Okay. So we quickly learned about how to implement the subtractor and comparator. Then let's learn about the ALU. So this is the arithmetic logic unit. Okay, so actually the arithmetic logic unit, so as you can see, so this ALU actually includes the different kinds of arithmetic and logic operation. And then this ALU is including the CPU. So it is because actually the CPU is similar to the calculator. Okay, so using a calculator, we just perform arithmetic operations, right? And the CPU is actually the same. The CPU includes the many instructions, but these instructions also perform arithmetic and logic operations. So like the A plus B, A minus B, A multiplied by B, A divided by B. So these operations are performed inside of a CPU. So actually the CPU includes the ALU, the arithmetic logic unit. Okay. Then how can we implement the ALU? So ALU needs to support the various types of arithmetic operations or logical operations. How can you implement? So actually, we can use multiplex box. And then actually for different operations, we need to implement the arithmetic logic for different operations. And we can select the final result using multiplexer. Okay, so like this. So ALU can support these different operations. So this is just an example. So actually the CPU ALU supports the many different operations, right? But in this lecture, we assume that the ALU supports addition, subtraction, and bitwise OR. So these different operations need to be supported. So ALU will receive two inputs, two input numbers, like it is the digital numbers. Okay, and then you can find the bit width of this A and B are N. Okay, and then based on the ALU control signal, this ALU supports the different operations. Okay, so you can find the ALU control signal here like 0, 0, 0, 1, 1, 0, 1, 1. So which means that if the ALU control signal is 0, 0, then it supports the add operation. So result of this ALU is equivalent to the result of adder. It's a 0, 1, it's a result of subtract. So this is the operation of ALU. So as I mentioned, in order to implement this ALU, actually, we can use the multiplex. Okay. So like this. So you can find the multiplexer here. So this multiplexer receives the ALU control signal. So it is because the ALU supports the different operations by ALU control signal. And then you can find that the result are generated by, so this is adder here, and then actually we can implement the adder and subtractor using a single adder, right? So as I explained, so the output is connected to the input of multiplexers. Also, you can find the AND gate here. So this is the bitwise AND gate, because if the AL control is 1, 0, then it needs supports the AND operation, bitwise AND operation. So this is the bitwise OR. And then based on the ALU control, then the output is selected from the adder. This is adder, and then sub. This is AND. This is OR. So ALU selects the one of four different result based on the ALU control signal. So actually, so it's not difficult, right? Actually, we can just combine the different arithmetic units, and then the final result are selected by multiplexer. This is just ALU, and CPU ALU also can be implemented like this. Okay. So as I mentioned, the CPU supports the various types of arithmetic and the logic instructions, and then in order to perform these instructions, we require ALU, but based on the different instructions, ALU just select the result by different arithmetic units. Okay, simple. Okay, so this is the some result of A plus B. Okay, so in order to support A plus B, then ALU control bit needs to be 0, 0. So which path is selected? This path is selected. Okay, so if we see this path, then we can find that this path is the output of adder, right? This adder. But also you can find that the ALU control bit 0, in number 0 is connected to the C in and then multiplexer of this adder. And then because this bit is 0, then it will work as the add. Okay, because the C in is 0, and then so because this 0, B is not inverted. So it's just add. Okay. So we can just analyze this ALU logic like this. Okay. And then CPU also needs to check the status, okay, using the flag. So if you see the ARM instructions. So we can find that the ARM instructions checks the status of instruction result. And then the status means that so it just check the if result is negative, okay, so it's the result is negative or not, or result is 0, and then or add product carry out or add overflow. So this status needs to be also checked. So for example, overflow. If overflow is detected, so which means that the result is incorrect. The CPU. So actually, this is the hardware. So we already learned that the hardware includes the limited resources. Okay, like the bit numbers. And then if the some result, arithmetic result is overflowed, then then the result will be incorrect. The CPU needs to detect this situation. Okay, then CPU needs to report the incorrect result to the operating systems. So CPU actually needs to check the status of result. Like so in this example, we just check the 4 different status. So negative, 0, and carry out and overflow. Okay. So AL just also generate these result. Then you can just implement these result this status bit like this. Okay. So carry is just carry. Okay. And then so negative, in order to detect the negative result, then we can just check the MSB. So as I mentioned, so we are the CPU is handling the 2's complement number. So we can check the MSB for checking sign. And then 0, you can just check the 0, 0, 0, 0, 0. So how we can use the NOR gate. Oh no. In order to check the 0, 0, 0, we can check the NOR gate. Okay, so this is because if we see the NOR gate, you can find that A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. Then what is the output of a NOR gate? It's 1, 0, 0, 0. So which means if we just use NOR gate, we can detect the 0. So in this example, this example just use the AND gate, but you can find that input is inverted, right? So it means this is a 0, 0, and then it's inverted, then it will become 0, 1, 1, 1, 1, and then we can use the AND gate, but it's equivalent to the NOR gate, okay, by the Morgan theorem, right? Okay. So also we can check the overflow. If the sign bit of result is different from the some correct result, we can check the overflow. So for example, we add the positive number plus positive number, but the MSB is 1, so it means it's negative. So result is incorrect because the sign is changed. But by checking this, we can detect the overflow. Okay, because the result is incorrect. Okay, so it's the same. So minus plus minus generate the plus, then it is also overflow. Okay. So ALU also detect the status of the result. So actually this is what I explained. then we can build the ALU like this. So you can think that, oh, the ALU design is as a rather complex because it includes the many logic gates and then also multiplexer and then some logics for generating data speed. But we can separate. We can separate the output because ALU generate the many different output. And then we can just design a certain logic that generates a certain output value. So for example, we can just focus on the overflow bit. So this is the overflow output. Then we can design the logic gate that can check the overflow. Okay. Then this is included in the ALU. Just carry the same. If the carry out is generated, then we can just detect that carry out carried generated. Okay, the negative and zero is the same. So actually, so we can design independent logic, and then this independent logic can be integrated in complex ALU design, right? Also, the ALU is simple because so ALU includes the different arithmetic unit or logical unit, but the result is multiplexed. Okay, so result is selected by ALU control bit. So actually, ALU is just the integration of what we learn. Okay. So we just focus on a simple logic, and then this simple logic is integrated. Okay, this is ALU design. Okay, so and then CPU, as I mentioned, CPU includes the ALU, the arithmetic unit, logical unit, and then the CPU's ALU can be implemented like this. Okay. So I believe you need to take the computer architecture course, right? The computer architecture. So in the computer architecture course, we will learn about the architecture of CPU. It's a very simple CPU, right? So you will learn about the ALU design also. Okay. So you need to remember this. Okay. So and then, as I mentioned, the CPU needs to support various comparisons. So actually, we can combine the status bit to generate the output of requested comparison result. Okay, so this table just summarizes the result. How can we utilize the status bit of ALU to generate the output of different types of comparison. Okay. Actually, but the basic operation of comparison is A minus B. Right. So by subtracting a certain number from a different number, we can compare these two numbers, right? It's a basic, right? It's a basic. So actually, for comparison, the CPU also performs A minus B, and then CPU checks is status bits, right? And then CPU reports the output to actually the output is can stored in the memory. Okay. So we can just add the different operations like the in this example different so we can add the set less than, so which means that so if the A is less than B, then result is 0 0 0 0 1, or otherwise result is 0. we can define some different operations, okay? And then we can also add the exclusive OR. Then how can we implement this ALU? So this is the ALU what we learned, okay? This ALU just to support 4 different operations, but we want to add the more operations. How? It's the same. We can implement the result for the required operations, and this result is multiplexed, right? It's the same exclusive OR. We can implement the exclusive OR logic, and then the output is also multiplexed. So selected by MUX multiplexer. It's the same, right? So actually, this example shows that it's a SLT is included, but in order to support this SLT, the ALU control bit needs to include the 3 bits, right? Because there are 5 different results. Okay. Then so you can find the new result here, and then also the new result is multiplexed by this 5 input MUX. Okay. So this is the ALU design. Then the other operation is shifter. So what is a shift? So if you are familiar with C, right? C has this operator. So what is this? It's left shift, right? And then also C has this operator. Okay? It's right shift. So bit numbers. So bits are shifted to the left direction, or bits are shifted to the right direction. And then C also supports this operation. And then we can frequently use these shift operators. Why? Actually, A shift left by 1. This is equivalent to A multiplied by 2. Right. And then also division is same. A shift to right 1, shift to right by 1. This is A divided by 2. So because the computers handle digital numbers, the binary numbers, so we can implement the multiply by power of 2 or divide by power of 2 using shift operators. And then shift operation is actually, so there are different shifters, different type of shifters, so like the logical shift operation, and then arithmetic shift operation, and rotation. So logical shift operation means that it's the bit position is just shifted. Okay. So this is the example. So you can find that it's a right shift operator. Okay. Then these bits are shifted to the right by 2 bits, and if these bits are shifted, then we need to fill the empty bits, and then the empty digit is filled with 0. Okay, this is the logical shift operation. And then arithmetic. Arithmetic means that actually, if the number, this digital data is a binary number, then and if this digital number is 2's complement number, then we need to apply arithmetic shift operation. So why? So in this example, this number like 11001 is shifted by 2 to the left, to the right, but we just fill zeros in the empty digit, right? But you can find that if this is the number, then this is the minus number, right? Negative number. But after shift operation, number is changed into the positive. So if we just apply shift operations to the 2's complement number, then the sign bit can be changed. So we can just, in this case, we can apply arithmetic shift operations. Okay, so it means MSB. When the digits are shifted to the right side, MSB is repeated, and then MSB is filled in the empty digit, empty bits. Okay, so in this example, the 1 is used, 1 is filled in the empty digit. Okay, but the left shift is the same. So 0, 0 is just included. Okay, so it is because in the MSB is the sign bit in the 2's complement number, but LSB is just the same. Okay, so we can also apply the arithmetic shifter, and then also we can apply the rotator. Okay. The rotator means that it goes to the right side, and then the left bits are filled up this empty digit. Okay, it's the different types of shifters. Then how can we implement the shifters? We can just use the multiplexer. Right. So just the location of a bit is changed. So in order to generate some output numbers, output bits based on some shift operation. So we can use the multiplexer for the different shift location. Okay, then can select the output because it just the location is changing. Okay, we can use the multiplexers. So as I mentioned, so the computers handle the binary numbers, so we can replace the multiplication and division operation using shift operations. Okay, for the power of 2. Okay, so we are learning about some different types of arithmetic units, but you know this you can just understand. I believe you can understand the basic design implementation method for these different type of arithmetic units. Okay, it's a multiplier and divider. So actually, we can apply the elementary level mathematics knowledge to implement the multipliers. Why? So it's the same. So because the number systems are different, but actually the basic operation is the same. So think about the decimal multiplication. So how can we perform this multiplication? So this is the multiplicand, and then multiplicand is multiplied by multiplier, right? This number, okay? This is the multiplier. And then in order to perform multiplication, we firstly perform multiplication between multiplicand and one digit of multiplier, right? And then the partial product, in this example, 460, partial product is calculated, and then for the next digit, we also perform multiplication. Then another partial product is generated, but the digit is different. So it means the 9200, right? And then partial products are added, so accumulated. That's how multiplication is performed in decimal numbers. The same is that it's the same for the binary numbers. This is a multiplicand, and then the multiplier. For each digit, we generate the partial products. Okay, like here. And these partial products are accumulated. Okay, and then we can get the final result. So that's why I said that addition. So actually, we are handling the binary number. Right? So actually, the generation of partial product is if the multiplier is 1, then this is the same to the multiplicand, right? And then if the multiplier is 0, then the partial product is just 0, 0, like this. So based on the multiplier value, then it's the same to the multiplicand or 0. These are partial product, and then these partial products are just accumulated, so added. So multiplier is just many adders. Okay, so many adders. Okay, so we can implement the multiplier like this. So as you can see, so you can find the actually adder tree here. Okay, and then partial products are generated by this multiplier value, and then the partial products are added by many adders. So these many adders are called adder tree. Okay, so many partial products are just added, and that's it. Okay, it's the same. Multiply is not difficult. Okay, we can implement the multiplier using many adders. And how about the divider? Division is a little bit complex, so it is because division includes the conditional subtraction. So what does that mean? Actually, multiplier is not to perform the multiplication. You need to generate the partial product based on the multiplier value like 0 and 1. And these partial products are just added. Just added. But when you perform division, the division is a little bit different because, so think like this. So when you learn about the division is more difficult than multiplication, right? So think about your elementary mathematics course, right? Division is more difficult. It's because we firstly check the division is possible. So which means that actually like the 5 to divided by 14. Okay, so, oh no, it's not it's 15. Firstly, we check the quotient is possible or not, right? So it's elementary math, right? So for example, so in this example, if we just set up if the quotient 4 is possible, but it's not possible, right? Because 15 multiplied 4 is 60, and then 60 is larger than the 52. So in this case, we just reduce the quotient number like 3, and then 45. 45 is smaller than the 52. Then we can calculate the remainder. The quotient is okay, and then we can calculate the remainder 7. That's the division operation. So it's in mathematics. It's the same to binary number. And then a good thing is that actually the binary number handles the 1 and 0. So which means that we can just compare the dividend using divisor for different location. So in this example, the dividend is 1 0 0 1 0 1 0, and then this is the divisor. Okay. The firstly, for this digit, we compare the magnitude of dividend, the 4 digit of dividend 1 0 0 1, and then 4 digit of divisor. So 1 0 0 1 is larger than 1 0 0 0, so we can get the quotient for this digit. Then subtract the divisor from dividend, then we can get the remainder. And then this 1 0 is less than the 1 0 0 0, so quotient is 0. Then also 1 0 1 is smaller than 1 0 0 0 is 0, like this. So in order to implement the divider, we firstly compare the dividend using divisor. So which means that we need to perform subtraction. Okay, but based on the subtraction result, then we really perform the subtraction like the 1 0 0 1 minus 1 1 0 0 0, or if the quotient is 0, then the subtraction is cancelled. So that's why the divider includes the conditional subtraction. Okay. So the division is more difficult than multiplication. Okay. So this is the decimal example, and then this is the binary example. Okay. And then this is the algorithmic flow. Okay. So, but anyway, we can implement the divider using subtractor. So which means, so we can also implement the divider using adders. But because of this conditional subtraction, usually division take longer time, right? It's more complex than multiplication. Also, it takes longer. So which means delay is longer or higher. So we will learn about the pipelining computer architecture course. So usually division is pipeline, but we will learn about the pipelining in the computer architecture course. Okay. Okay, so this is the end of this part. Okay, then I'll briefly explain about the sequential building block. So we don't have enough time, but it's okay because I will explain only about the counter and then shift register. Okay, only two logic. So counter means that, so actually for every clock edge, the counter means the number is incremented by 1. Okay, so then how can we implement this counter? We can implement the counter using adder. Right. So it looks like this. So this is the implementation of a counter. So you can find that adder is here, then the if flip-flop is here. So I mentioned that the definition of a counter is that the output value is incremented by 1 at every clock edge. Okay, edge. So you can find that this is the output of counter, okay? So Q, and then you can find that this Q is feedback to the input of adder. And then another input of adder is 1. So what does that mean? So this is it's a Q, it's a deep reply, that's a Q, and then it performs the Q plus 1, okay? And then this Q plus 1 is sampled by the next rising edge of clock. So which means the number is increased by 1 at every clock edge. So this is the counter. And then so counter is also frequently used, but we can implement this counter. And then if we just change this number, we can implement the different types of counter. Okay. So this is also the counter design. So you can find that at every positive of clock, then Q equal Q plus 1. Right. It's simple. Then this is the more verbose design. Okay. So in more verbose design, I use the Q next node. Okay. And because this is the combinational logic part. So if you see the counter implementation, you can find that adder, and then adder is also combinational logic. Okay. So this is the combinational logic part. Then the Q next is updated to the Q, the rising edge of clock. Okay. So then shift register. So shift register is just the series of registers. Okay. So this is the implementation of shift register. So you can find the registers here, okay? And then this is the input of shift register. And then you can find that the output is connected to the another register. The register is the multi-bit flip-flops, right? So shift register means that the data is input to the first register, and then at the 1 clock, the data is propagated to the next flip-flop. Okay. So this is the shift register. Okay. So it's a very simple, actually. So the data is shifted by 1 on every edge of clock. This is the definition of shift register. So sometimes we need to control the timing of signals. And then I mentioned that in digital systems, we can control the timing using clock signals and deep flip-flop. Because the deep flip-flop, in the deep flip-flop, the output is synchronized with the clock. So using the shift register, we can delay. We can make the signal delayed by a certain clock. Okay, clock numbers. Okay. So this is some parallel load. So which means the actually when the load signal is enabled, then new values are just updated to this deep flip-flop. Okay, so you can find the multiplexer here. Then if the load is 1, then new values are loaded to this shift register. Okay. And then by using shift register, then we can make the linear feedback shift register. It's called the LFSR. Okay, so this is the implementation of LFSR. So LFSR is used for generating pseudo-random numbers. As I mentioned, pseudo-random. It's not entirely random. It's pseudo-random. Okay, so and then actually the random numbers are repeated. Okay, so this is the another application of shift register. Okay, then this is the system value implementation of shift register. So actually, so it's a shift register with parallel load. So as you can see, the reset, the output is 0, and then if load signal is 1, new value is loaded to the shift register. And then else, if load is 0, you can find each bit is shifted like this, and then new bits are loaded to the first D flip-flop. Okay, so try to understand this implementation. Okay, so as I mentioned, this part is very simple. So and then so I explain about the let's see, counters and then RFS shift register. Okay, so oops. Wait a second. Sorry, just a second. So I will close this course. Okay. So we learned about so in this course I covered these topics. Okay. So I hope you can understand and then remember these topics. Okay. And then what's the next part? So and then in the computer systems we cover these layers like logic and then gate level layers, right? Now what's the next layer? So next step is architecture layer. And then I believe you can take the computer architecture course in the next semester, right? As we call, this is the mandatory course, right? And then so okay, you can take the computer architecture course, and then the next semester. Then so I may teach the computer architecture using this book. Okay, so it's done, and then thank you for your support, and then so thank you for your attention for this course, and then look for your final exam. Okay, 감사합니다.